Hello, I'm Mr. McBrien. This is SCH4U, Rates of Reaction. The Ontario curriculum would like for us to be able to investigate and analyze energy changes, but also rates of reaction in physical and chemical processes, and solve problems related to that. Today we're going to focus our attention on basic rates of reaction and the reporting associated with it. So we've already, in the beginning of this unit, talked about the question of whether a reaction will take place. And really that's the concern of thermodynamics. Kinetics instead focuses on the idea of if a reaction does occur, how fast will it go? Rates are extremely important to various aspects of chemistry and biology. In industry, we need to be able to control the rates of reaction if we want to have a safe factory, but also if we want to get product out to our customers. Metabolic processes in biology determine, for example, if a drug will be effective or if it'll be fatal. And in nuclear reactions, we can see reaction rates on a scale of microseconds in the case of an atomic bomb, or millennia in terms of carbon dating. The capacity to be able to effectively measure, report, and control rates of reaction is extremely important. So what is rate? The reaction rate is a measure of how fast a reagent is used up or how fast a product is produced during some given time frame. Now, when we're measuring these changes, we might measure the changes in mass, for example, of a piece of iron. We might measure volume of a gas, pressure of a gas. We might measure the color of a solution. We might measure conductivity. But in all cases, what we're really concerned with is this idea of concentration. And so we'll most commonly concentrate on this idea of concentration. So if we want to define rate in terms of concentration, then it's the change in concentration divided by the time period of interest. So let's take an example to illustrate this. So if we have the reaction to produce nitrogen dioxide and we want to measure the rate, we might measure the amount of nitrogen dioxide. In this case, it goes from 0.32 moles per liter to 0.8 moles per liter. And the time frame of our experiment is 3 minutes. Here's the balanced reaction here. Nitrogen gas reacting with oxygen to form nitrogen dioxide. Now, so we've been given our initial concentration of nitrogen dioxide and our final concentration of nitrogen dioxide, and our time frame under which we work. So this is really a pretty simple calculation as long as we keep in mind that we need the change in concentration over the change in time. So we can then lay out our equation. The change in concentration of nitrogen dioxide is just 0.8 moles per liter minus 0.32 moles per liter. And of course, delta T is 3 minutes. And plugging this into a calculator, we get a rate of 0.16 moles per liter per minute. Don't forget units. The units are important in rates. Okay. So that's very interesting. It is worth noting, though, that we also could have expressed the rate of that reaction in terms of nitrogen. And here's where something gets very interesting about reporting rates of reaction. We have to consider stoichiometry, and we have to be careful what we're reporting in terms of. So let me illustrate this by actually converting our rate of production of nitrogen dioxide to our rate of consumption of nitrogen gas. So the rate in terms of nitrogen is negative the rate in terms of NO2 times the molar ratio. And this is good that we have our equation up here so we can see our molar ratio explicitly. So if we plug into this equation then, our rate in terms of NO2 was 0.16 moles per liter per minute. We put a negative in because the nitrogen is being consumed. And then our stoichiometry, it's 1 mole of nitrogen for every 2 moles of NO2. And plugging that in, we get a rate in terms of nitrogen of negative 0.08 moles per liter per minute. Once again, remember that the rate is negative because it's a reactant, because it's being used up. So let's illustrate this graphically then. So if we take some generic reaction and we look at our concentration versus time for this reaction, we can see that reactant A, the dotted line, reactant A starts with a high concentration and drops down as the reaction goes on. Product B, the dashed line, starts at 0 concentration and increases over the course of time. And then eventually they reach a point where the reactions no longer proceed. So this is pretty easy to rationalize. The reaction starts fast when there's lots of reactants and no products, and then slows down. Now we usually measure the rate somewhere close to the beginning of the reaction. And in this area, the rate can be taken as roughly linear. But notice what's going on here. The product rises very quickly at first and then slows down as the reactants are used up. The reactant A falls very quickly at first and then slows down over time. Now if we wanted to measure the rate, we could measure it directly off of this graph. The average rate would just be the slope between 2 points. The instantaneous rate is the tangent of this curve at any time. Okay, so what are some of the things that affect rate? The rate will be dependent on temperature. It'll be dependent on the concentration of the reactants. It'll depend on whether a catalyst is present, and we'll bring this up again in a little bit. It'll be dependent on surface area, and this will come up again. And of course the rate depends on the chemical nature of the reactants. So let's take a few seconds to investigate these factors and how they affect the rates of reaction. So temperature, we need to think about what has to occur. What conditions are necessary for a reaction to happen? Now, increasing the temperature of a gas or a liquid increases the speed that the particles within that sample move. Now, greater speed increases the chance that two reagents that are involved in the reaction will have a collision. But further, those collisions will be faster. Because the motion is quicker, the relative motion of the molecules will be greater, the kinetic energy will be higher. And this increases the chance that contact between these molecules will be effective. As a result, it's typical to see the rate of reaction double when you increase the temperature by 10 degrees. So this is a rule of thumb, but it's generally pretty effective. Now, it can't work indefinitely, of course, because eventually you see phase changes for given samples. But it's a good rule of thumb. Now, as far as concentration goes, if we increase the concentration of the reactants, this increases the chances that there's going to be a collision between the necessary reagents. So the rate is generally proportional to the concentration. However, this is dependent on reaction mechanism. There will be more on this later. Surface area is an interesting one. We don't normally think of wheat flour as being explosive, but in fact, as a result of high surface area, flour can be exactly that. So, May 2nd, 1878, the largest mill in Wisconsin was working away grinding flour, and there was an explosion that leveled the building and actually resulted in 14 people losing their lives. Now, the reason why flour could become explosive was because its surface area is so high when it is ground very fine. And this goes back to this idea of contact between reagents. So in this case, there was much greater opportunity for the flour to be in proximity to the oxygen that was needed to make it explode. When we increase the surface area, then the opportunity for contact between reagents increases, and we can see dramatic increases in rates of reaction. The reaction type, no great shock here. Some reactions are faster than other reactions. For example, this oxidation reaction just simply involves the transfer of an electron that can travel theoretically at a speed approaching the speed of light. It's an extremely fast reaction. In contrast, the reaction between nitrogen and hydrogen involves the breaking of chemical bonds, and it's much slower. And there's no great mystery to this. Now, in terms of catalysts, we'll talk about this more in the coming days. But for now, it's easy enough for us to realize that since the rate of reaction is dependent on the type of reaction, if we can add some additional material to our mix that changes the type of reaction, it stands to reason that the rate can change as well. And in fact, that's what catalysts do. They change the reaction mechanism, the way the reaction occurs, and as a result, they change the rate. So to summarize, rates of reaction are important wherever we have reactions. We need to be able to measure, we need to be able to control rates of reaction. We express it in terms of change of concentration divided by elapsed time, but it can be expressed in terms of the reactants or the products. So we have to be careful to specify in which terms we are giving a given rate. We can control conditions in order to control the rate of reaction. So this is a very important point in various aspects of chemistry, the ability to control the rate of reaction. Okay, so for the homework, there's a nice worksheet on calculating rates of reaction, and be sure to review today's note for any additional details you may have missed. Thanks very much, and have a great night.